something does in fact not quite work, then I believe you all have a bit of experience from this amazing guy right here, so I'm sure we can work it out together. But yeah, thanks for that introduction. I'd like to give you a bit of a whirlwind tour about some of the cool things you can do with SDR and some of your newfound knowledge. I'm basically trying to create cool applications at Edis Research. And actually, while I talk, I just thought I've got these here. Just pass them around to have a look at. Start them off here, and I'll be talking about both these radios. Is the camera recording? Cool. Now you can just sort of have a bit of a feel and to see what it looks like. So today I'd like to talk to you about a couple of different areas in software-defined radio, how we can apply the technology. Spectrum monitoring, aviation radar, I believe. Can you show your hands if you've mucked around with ADSB? I thought that was a bit of a lab component, so you're all sort of familiar with that. That was the very first thing I got into when I discovered software-defined radio. Restaurant pages, some other interesting applications, and the ISEE-3 reboot mission. Did anybody hear about that old NASA space probe that people got in contact with? Yeah? All right. So a little bit about that. And much of this stuff is actually done with GNU Radio. Who's heard of or used GNU Radio? Yeah, everyone. Is that like a core part of the course? Yeah? So you know about it. It's a really cool, open source, powerful SDR DSP framework. I won't go into the details, but if you want to get into this later on, definitely check it out. So the first thing is spectrum monitoring. Now, I'm sure you're all aware of the radio spectrum. Can anybody sort of take a guess as to what part of the spectrum we might be looking at on this waterfall? Everyone sort of is clear on how to read the waterfall, right? So you've got frequency across the bottom, time across on the vertical. Any guesses to what we might be looking at here? Any guesses? Anything at all? Cell phones. That's it. Yeah, that's right. So we've got narrowband 2G GSM in the middle, and then we've got some wideband, probably 3G stuff on the left and the right. So the cool thing about modern SDR is that you can actually pull in an enormous amount of bandwidth over modern interfaces. So here, this is actually using that B200 or B210 board that's being passed around there. That's the whiteboard. And this is connected to the computer via USB 3. So it's a little bit faster than... you guys have all been using RTL dongles as well, right? Yep. So that's USB 2. Here you can pull in 50 megahertz worth of bandwidth at one time, streaming. This program here is called Boardline. It's one of my favorite signal analysis tools. If you want to get into it further, then definitely download it, check it out. It's free. It's really, really powerful, and it lets you sort of peel back the layers on signals. And in this case, this is actually streaming over 10 gigabit Ethernet from another device. This is 100 megahertz worth of bandwidth coming in at once. And we're looking at the 400 megahertz band here, which has got a whole lot of narrow band signals, utilities, trunking control channels, telemetry, and so on. So it's really cool to be able to see all these things fly past. That's real time. Yeah. So everything here is real time streaming. So in terms of monitoring the spectrum, it's interesting to actually see what's out there, see what sort of signals occupy different bands. And if you want to know which car is mine, it's always usually the one with the antenna sticking out of the roof there. So here I was driving around near Las Vegas, got some GPS antennas so the radios can track my position, and also the different antennas which will be used to scan the radio spectrum. And then if you look in the back of the car, you can see there's the laptop and a couple of SDRs hooked up that'll be doing the sampling. And I just wrote some simple Python code. It's online open source on my GitHub. You can run that on your computer, program in what parts of the spectrum you want to monitor. If there's energy there that will exceed some threshold, you can log it to disk and review it later on. And the cool thing about it is that apart from just sampling the radio frequencies, because you have a GPS there, you can actually spatially tag every time you record some of the spectrum. So you then can do maybe surveillance, or you can do regulatory stuff to see whether transmissions might be legal, or whether you might have interferers, transmitting into frequencies they shouldn't be, and so on. And so the Python code runs in the background there. It just tells you what it's doing, and then it gives you an FFT to show you where the energy is. Again, it's looking at the cell phone band, so you can see all sorts of different transmissions there, and it'll just step through. So this is the board that's actually going around. It's pretty neat because it's USB 3. You plug it into your laptop. and it's powered by the laptop, you can actually stream up to 56 megahertz worth of bandwidth in real time, and you can cover 70 meg to 6 gig, which is quite a broad frequency range, covers pretty much everything. And you can do 2x2 MIMO. So this is cool, and if you get one of those RF up converters that will take, say, HF up to 70, above 70 meg, then you can basically listen to the entire radio band. So it's pretty cool stuff. Now, I've got a couple of demos here, and the demo gods willing, we can actually try some of it out. The first thing that I wanted to show you here is, let's see if this loaded properly, is, has anybody used HDSDR before? Yeah, a couple of people. SDR Sharp? Yeah. GQRX, right. That's a good one too. So this is now just streaming from this radio here, and I have unwittingly connected the wrong antenna. So if I do this, then we should be good. Has anybody brought their Baofeng along? Yeah. So you want to tune up around there and say hi, but do it at a low power level if you don't mind. 8 watts. Well, I've got an attenuator on this as well. So obviously, you've probably all seen this. I'm transmitting FM. This is Victor Kilo 2, Foxtrot Uniform November Kilo, CQ. And there's my FM modulated transmission. You're all familiar with this, right? You've all seen this kind of stuff before. So that's pretty straightforward. Oh, there we go. Yep, that's a little bit more powerful. Now, in addition, we've been using our little HTs, but can anybody see something on me that might also be transmitting a wireless signal? My wireless mic. So I didn't have quite enough time to find it. However, let's see if we can't actually find it now. It should be in 500 or 600, yeah. Is anybody else able to help me out with finding it? Anybody scan around? Bandwidth. Well, they're configurable, so you can actually change the... I'm going to up it to 4 megasamples per second, and then should be somewhere around here. If we can't find it, then we can try it at the end.
Yeah, there you go.
Is that me? I don't think that's me. Test 1, 2. It's something else. It looks interesting, though. This is kind of the fun thing. You can just scan around and find interesting signals and then decode them. And I'll show you a couple of examples of that. Does anybody have an RTL dongle with them or a radio with them they can find my transmission with? Test 1, 2. Is that me? Test 1. No, that's something else. Anyway, let's come back to that. I'll show you a neat little trick you can do.
On the back, it actually, what it is.
Oh, is it? Oh, I beg your pardon. You're right. It has the range. So 554 to 590. That certainly helps. 5, 5, 4. With a bit of luck. This thing is actually on, right? Yeah. Come on. There we go. That's me right there. So what do we have? We've got approximately 57775. All right. Let's remember that frequency. This is where the fun begins. Unfortunately, I can't show you the screen of this laptop, but I'm running GNU Radio, and it's running natively on OS X using Mac ports, which is a nice sort of Unixy emulation layer. And I've got a flow graph open, which is named something wireless mic. So I'm just going to load that radio up. And the demo gods are not willing on this one. You know that board that I was passing around? Does anybody still have that? Can I have that one? This one's not playing nice at the moment. Thank you. Let's see how many of you had a good static charge on you when you were playing with it. Oh, that's not working. All right. I don't know why it's not working. That can go back into rotation. Okay. All right, we'll come back to that. But at least we found that there. So the other thing I wanted to show you is these are all analog signals, right? But there's plenty of digital signals out there too. And one of the digital radios that we use on a daily basis is your mobile telephone. So if we look at another frequency, say 945.2, which is this one, this is actually the downlink signal of a 2G GSM base station. Would anybody hazard a guess as to where that base station might be? That's right. Someone's pointing over here. And you're totally right. This base station is actually running on this desk from this little radio here. And to boot, it's actually running off this battery pack. So you've got a fully portable mobile phone base station. And so this device here is actually both an SDR and an embedded computer. So it has a dual-core ARM with an FPGA fabric, and it's running OpenBTS, which is an open-source implementation of the 2G GSM spec. So if you actually get your mobile phone out now, if you have an unlocked phone, you're welcome to play along. If you put your phone into manual carrier selection mode, so you do the manual network search, have a look for a network that you mightn't expect to see in the list. Now, I suspect there might be somebody in the audience that actually might already be on the network with their phone. So I'm just going to try giving them a call. And also over here, I'm going to bring up the SSH session that I have open into this base station. So every time there's some activity, like a text is sent or a phone call is made, you should see something scrolling there. Now, I'm going to switch the frequency so that instead of looking at the downlink, we're going to look at the uplink channel. So we're going to see any activity that is sent from the mobile telephones. So we should see something there if something happens. Let's have a look. I'm going to try making a call. You can see there's some activity going out, and there's some activity here. Call failed. So there is one caveat to this demo. If the audience is so enthusiastic that everyone gets their phone out to log on the base station, it might have a bit of a problem. Oh, something's happening. It's calling. Oh, who's that? Hello? Let's try that again. I think too many of you are on there. Unfortunately, it can't handle an excessive call volume. But you can see there, as the call is established, the setup, call setup, and the actual transactions all result in digital communication, which is why you can see that activity on the spectrum. Hello? Looks like it's working. Cool beans. Yep. Goodbye. Now, has anybody successfully been able to log on? Yeah, what network do you see? Could be it. Thanks. Yeah, just chuck it there. Thanks a lot. Yep, that might be it. Were you able to log on?
Yeah, it gave me an INSI.
Yep. So what you can actually do now is you can call me, if you like. Actually, my phone number has changed because I put a different SIM in here. But if you dial 2101, you can actually establish a call. If you text back a number to 101 that sent you the original text, you can actually nominate your own number on the network. As long as it's 4 digits or more, you can make your own number. Oh, there we go. And then... So, does anybody want to try 2109? I sent that number back, and we can do a test to see whether it works. We can coordinate that, no problem. Oh, no, it's working. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a very original phone number. Hello? Hello, hello. I think. Oh, there we go. Hello. There we go. I got a text. Somebody sent me a hey text. Who was that? Who was that? Oh, yeah, cool. So it works. So you can do texting. And if you can't hear me down the back, you can call me and then get the slightly delayed version of my speech. So you can send texts as well. So by all means, if you have any questions throughout the presentation, you can put your hand up. But if you're a little bit shy, then feel free to give me a call or send me a text as well. So, what I'm trying to show you here is that you can do this kind of cool stuff. You can prototype this sort of technology on these reconfigurable radios, but then have it talk to commercially deployed and commercially available gear. So it's really powerful stuff. So
We have one of these for the shop.
So let's move on from that. And if there's a little bit of time at the end, we'll come back to this thing because it's a bit of fun. I don't know why my laptop's acting up. Question?
Yeah. Are you meaning this to be like future technology that you might use in crowded scenarios, or is this just playing around?
Well, this is more sort of playing around so you can get an idea. But you meant in crowded scenarios.
So a lot of times you don't get good service if you're like at an
Right. Yeah, so actually what a lot of providers do when there are those sorts of events is that they ship in additional cells to service that area. And you can often spot them because they'll be put in some relatively odd spot. They'll have a tall mast there and they'll have some big generator and some box. But with this kind of stuff, yeah, you can deploy this, but also you can there's 3G and 4G, right? LTE. So somebody has actually written an LTE base station that will also run on this gear. And has anybody heard of Fabrice Bellard? He is this amazing French programmer that has done all sorts of incredible things. He broke the world record in the computation of pi on his desktop computer. He wrote single-handedly this 4G LTE base station to run on software-defined radio. He authored FFmpeg and QEMU. Any of these things ring a bell? So a prolific, amazing guy. But yeah, he actually wrote the LTE thing. So now I'll show you a couple of interesting things that I've played with in the past. You've looked at ADS-B. A typical 747 has lots of radios on board, and that makes someone like me really happy. Did I take that slide out? Oh, I have to bring it back for you. Oh, no, I rearranged it. Sorry. This is an update. So yes, as I was saying, a 747 has lots of radios on board. And if you fly next time, then you can actually look at the plane next to you and try and identify all the different antennas that are on both the top and the bottom of the fuselage. So there are lots of different things going on. But that, if you have an SDR, then that can make someone that likes software-defined radio really happy. I do not recommend that you do this. I don't know if you read in the news recently, but there's a security researcher that made a tweet about jokingly setting off the oxygen masks by hacking the air gap through the Wi-Fi. He was pulled aside by 2 FBI agents just before boarding the plane, and he had his equipment confiscated. They have since issued guidelines to look out for people with excessive wiring or wiring into the entertainment system and so on. So just be wary. Pardon? No. So there's the primary surveillance radar and secondary surveillance radar. You might recognize this big radar that you've seen at the airport. The primary surveillance radar is the traditional one that sends out a pulse and waits for echoes from metallic objects like fuselages of planes. And the secondary system actually will ping a transponder, which has to be on the plane, and the transponder will reply back with things like altitude and squawk code and so on. So that's an active system. And if you look up one of these radars, then you can see that actually it's rated about 17,000 watts, so quite a bit of power going out there. And it covers quite a broad area. This is the one in Sydney, where I'm originally from. And you've played with ADS-B, so you know that it sends out all sorts of really cool information automatically. And this is my friend back in Sydney. We would go to a hill above Sydney Airport and take all our laptops and our SDRs and set up there and receive all the signals as I was developing my version of the decoder and mapping software. And then we could see the planes flying and landing and taking off, and actually then compare that to what we saw on the screen to make sure that it was working. So good times there. But if you write one of these things in GNU Radio, this is the scope plot that's actually showing you the AM signal received from the transponders. So you can see that there are lots of packets being decoded there and lots of varying signal strengths because, of course, they're coming on the same frequency from all sorts of different planes at different distances. And if you plot that, then you can obviously start seeing where they are. So I understand that you've done some plotting of the positions as well? Yep. So this is some software I wrote a while back, and this is the Bay Area, and you can see all the planes coming in landing at SFO and SJC and Oakland. And it's cool because also the trails are color-coded by altitude so that you can see when they actually come in. Now you see this butterfly effect. Sometimes transponders are actually not implemented properly, and they essentially end up transmitting garbage. So when a decoder is implemented correctly, it will decode the garbage as this sort of pattern. Did you ever see any of that? Occasionally you get these bad transponders popping up. If you zoom in, it's kind of neat because you can see all the flight paths. So here they're landing and taking off at SFO and so on. It's just, and then here you've got some other interesting tracks. This is actually now SFO. Somebody's landing there. Somebody's flying overhead. And I went down there and took this gear and watched the runway from the car park nearby. And so you have this parallel approach now. And you can see how they're green. When it turns red, that's when the nose gear is actually touched down on the tarmac. So it switches from airborne messages to surface messages. And now that other plane is touched down as well. And so you can see them there, and they'll taxi over the runway. And I don't know about you. I think for most people this might be pretty dull, but I find this so exciting because it's a real-life system, and it's supposed to be safety critical and so on. And it's kind of cool to watch it in action.
Are you seeing are most of the planes running this?
A lot of planes now, yes. I mean, the FAA has mandates to spread this throughout modern aircraft. Interestingly, the US has been kind of late with the rollout compared to other countries. Australia has been far more successful at deploying them in all sorts of aircraft, even sort of domestic carriers as well, but it's been slower in the US. But as you can see, there's a lot of traffic. So here we've actually had a Virgin America flight takeoff, and it's following this trail left behind by a previous flight. Look out to the top right. But that's okay because you can see that it's a wildly different altitude. So everything's all safe. Now, I always sort of consider this stuff from a security perspective as well. And this is something that you all should consider going out into the world when you're thinking about this sort of technology. Security is actually really, really important. And this is one instance where security was not at all considered in the original implementation. So this is a decades-old spec. It's been rolled out in an enormous number of airliners around the world. It's very expensive to do so. And so if there's a problem, then you can't really just go and apply a software patch to all these different planes in the sky. This is an example, and you'll see some others, of a protocol which is essentially completely insecure because it's got no encryption, there's no authentication, it's completely out in the open, which is why we can so easily decode it, right? But the problem is if you can decode something, then it means that if you're, a bad person, shall we say, this hardware is so cool because you can equally create your own transmitter. So just like I've created my own mobile phone base station, you could potentially spoof aircraft. There's no reason why you can't implement the spec and then transmit your own phantom signals. And so this is a really interesting case study into the vulnerability of this technology and then how the government and regulatory authorities and the FAA respond to this. And they don't really respond terribly well. But we need some open dialogue between all these parties to get things moving in the right direction. Because you have altitude, you can also map things in 3D in Google Earth. So I took a little step further and make this web-based streaming thing. That's that same Virgin America flight taking off, but in 3D. And so we can zoom out a little bit, see the whole of the bay. Again, that flight is coming in the top right. Somebody's coming in there to land at Oakland. And then you can also take all that information and create the virtual cockpit view so that you can be in the position of the pilot pretending to fly the plane and get a sense of what taking off is actually like. And if we let that run for a little bit, we'll swing around to the north, and then you can see San Francisco in all its Google Earth rendered glory there. This was when I actually had one of these tucked into my seat pocket, in the seat back on the plane, without an antenna. If you consider under my butt, there was a 250-watt transponder antenna, so I didn't really need my own antenna. Bit of a rough landing into SFO, and Google Earth started doing all these really weird extrusions of the terrain to do their fake elevation map. It looks like you're taxiing through burnt-out fuselages at SFO. Pardon?
You have to go build the structures.
That's right. Yeah. And then, so they're the transponder transmissions. This is looking at Sydney Airport now from a slightly different angle. It's kind of nice to see. You've got the parallel runways there, all the pretty patterns that occur. You'll notice that you'll see it in the next video, but you see how all these dots are now appearing on the lines? This is a different wireless protocol that's used by airlines. Has anybody heard of ACARS? Yep. ACARS is the Aircraft Communication and Reporting System. You can think of it like text messaging for aircraft. So instead of the transponder sending this stuff out, this system is used to communicate between the pilots and air traffic control, send waypoints to the plane. The engines will send performance reports automatically back to Rolls-Royce about vibrations that were measured during a flight, diagnostic information, engineering information, all sorts of interesting stuff. And a lot of it is... Pardon?
136.
Yeah, that's right. So in the 130s in the VHF aviation band, you can find these transmissions. And a lot of those messages are actually sent during takeoff and landing and taxiing, which is why here, if you look, you can see that a lot of these dots actually occur at around this time. So each dot on this map is an ACARS transmission. The system is able to automatically link the transponder stuff with the ACARS stuff and then show you spatially what's going on. This is a view of the broader area there. Every single time there's an ACARS transmission, it will show you the contents of the message in a balloon that pops up. And this is also an interesting study because a lot of this stuff is human readable. So there's very few stuff which is I don't think any of it's really encrypted. Some of it's sort of obfuscated, but you can usually make sense of it, and you can see how much fuel was used up, or engine pressures, and all sorts of interesting diagnostic information if you're that way inclined in aviation. Now, there is one thing. Every single time I would look at these ACARS messages, for some reason I would always notice that there were messages about clogged toilets on aircraft, or that the galley was flooded. And so I thought, why not use this? Make a little Easter egg, so whenever there's a blocked toilet, use this icon instead of the little colored dots. And then, in addition, the waypoints can sometimes be sent to and from the cockpit. And then I loaded a waypoint database. And then it was just interesting to see the flight paths that the planes would follow that would be sent those coordinates. So these planes are going into Asia, long-haul flights into Asia, and then these ones are going to the west coast of Australia. That's the secondary system. I thought I'd also look at the primary system. So I went out to Moffett Field Air Force Base, just south of here. They have one of these ASR-9 primary surveillance radars that rotate there. And I took one of these B210s with a little whip antenna and just held it up there. And every time you can see the radar come around, you can see this massive pulse of energy. What caught my eye, though, that was interesting, was that this scope plot is being triggered by the initial transmission, the initial bang that the radar sends out. And then, if you look carefully, you see how there are these small energy signatures that show up immediately after the bang. I thought, well, hang on a second, what's happening here? This is energy that's being reflected off objects nearby. So this is usually called clutter, because you're interested in stuff that's further out, like aircraft. But it was just interesting that that was there. And so if you actually look at the radar return, you've got the bang that the radar transmits initially, which is this big pulse. And then you've got the echoes that come back off objects. And you can see that there are some echoes coming back along here. Now, I took that data and I wrote some a program to process that. And actually it produces this raster plot. So vertically here, you have time, but every scan line is triggered by a radar bang, a radar pulse. And then it just keeps recording the information that comes back to the radio. And you can immediately see that there are these interesting shapes that form. Remember, I'm receiving this with one of these radios and a whip antenna. I'm not using a big high-gain antenna like the radar is. So if you take that and then unwrap that onto the map and position it over the radar, it actually lines up with physical features in the bay. So what caught my eye initially, you see how you have this curved shape here? When you do the polar unwrapping, it becomes straight. And this actually is the power line pylons that cross the water of the bay. So they're reflecting the radar energy back. And then you've also got the bridges here that reflect some back as well. And then you've got sort of larger structures around there that do the same. Now, this was interesting. Yes?
Yes, you just took the rectangular image and you wrapped it around a particular axis. And
Yep.
you could match that up.
Exactly, yeah. It was, I mean, it would be nice to do it automatically, right? But I just used GIMP and did the unwrapping and positioned it. It's a pain, though, because you have to scale everything appropriately, and then, but, you know, eventually you can get it there. What I did then was I recorded multiple rotations of the radar. So if you think in your head, if you take, say, I think I could capture about 6 rotations because I was recording at 50 megasamples per second to RAM disk on my laptop. And so I'd run out of RAM. But I took the first rotation, one of the middle ones, and the last one. And the first one I mapped into the red channel in my image. The middle one I mapped into the green channel in my image, and the last one I mapped into the blue channel. And so what you expect to see is everything that's static and not moving will be white. But anything that moves, you'll get an RGB triplet forming, and you can see one right there. So when I was capturing this stuff, something was actually moving in the space around me. And so if you unwrap that, it neatly fell into this portion of the bay. I don't really know what it was. My theory is that it might have been a truck, judging from the speed that you can derive from the radar rotation and the separation here. It might have been a truck moving along a bay there, the bay. And if you consider a truck, if it's turning into the radar, the side of the truck will have a nice radar cross-section to reflect the energy back. Just a theory. I don't know. So this is something else, restaurant pages. I'm sure you're all familiar with these pages. Yeah, question? This one? Here, these ones. These ones? Yep. So they are just poorly synchronized returns by the software. The software attempts to detect the beginning of a pulse and then align everything appropriately. But here, especially if you do a polar unwrap, it will exaggerate any misalignment in the data. And because we're looking at multiple rotations here, it just happens the way they fall on one another is just slightly off, and so you get this coloring effect. And also, I think there are different effects that come into play that means that each recording will be ever so slightly different with sort of these large features. So, you know, when you go to a restaurant, you can order some food. They give you a pager. It goes off when you have your order ready. You can go and collect it. So the order and collection rate should be the same unless, for example, all the pages in the restaurant are set off at once. So you can figure out what frequency is being used by looking at the back of the pager. You can visit the FCC's website to look at the frequency, or you can actually just scan the spectrum like we were doing at the beginning and find the transmission. What you're hearing there is actually a page going out and setting off the page. So, long story short, you can actually receive the data, do what's called blind signal analysis. So remember, you're coming at this without any information about how the radio signal is modulated. You can use various techniques in GNU Radio to peel back the layers and figure out what the baud rate is, what the deviation in the frequency shift keying is, all this sort of stuff. And then you can extract the raw ones and zeros. Once you've got your raw data packet, you can then figure out where the pager number is encoded in that. So what you do is you can compare different transmissions to see where the data bits are different, and then get your own order, see when that's paged, and then actually you can neatly figure out where that's encoded in the packet. Now, in addition, it's also nice to know how the CRC or the checksum is computed for the packet as well. And in this case, you add up all the bytes, mod it with 255, and then you get your checksum byte. Now, if you have all of this information, what can you do? So this is Matt Edis. He founded Edis Research. We all went out to lunch, and I said, I'm just going to collect some more data. Little did my colleagues know I had a working system. I had everything outside, and I said, I'm just going to the bathroom. So I had a a Wi-Fi interface on my smartphone to set it off outside, and I had looked up his number. And this is a really interesting social situation too, because the expectation is when your beeper goes off, your food is ready. So he's confused. The poor lady behind the counter's confused. Mayhem. And, of course, as soon as I turn up with my little GoPro, he knows that I'm up to something, which is why he always says, "Oh, you're making me nervous." So he figured it out. So that's one pager system. There's another pager system that uses the protocol that the old beepers used to use. And you can get some code for GNU Radio that will decode that. And once you reverse that, then you can do this.
You can see it going up there. And once this goes off, and then we'll do 39, and then we'll do 56, and then we'll do 83, and then 82, and 78.
$56 didn't go off because I had to tweak my transmitter a little bit. There's a third system that I discovered. This is really neat. These pages actually they are given to you when you order. When you go to sit down at the table, underneath the table is an RFID tag. So when you place these pages on the table, they read the tag so they know where you're sitting, and they will transmit back to the kitchen this information. So they bring the order to you, but since you haven't told them where you're sitting, they can actually know your table number and bring it out. So again, this is all hooked up. These actually use Zigbee, so an 2.4 gig ISM band. You can use a GNU Radio decoder, which is really fully featured to receive the signal, put it into Wireshark. Who's used Wireshark before? Yeah? So it lets you dissect these protocols. And what do you know? All of the numbers match up within the packet. Oops, sorry. So you've got the two pages. And I went around the back of the kitchen and peered around the back of their screen to see what table number we were sitting at, and that was this one. And then they're just there in the packet, wide open. So another thing I've been looking at recently is drones. I don't know if any of you are interested, but I actually brought one right here, and we can go and fly it afterward if there's time and no conflicting arrangements in the park.
Is that in the marina?
Yeah.
When you do the competition?
Yeah. No, I don't. I just went there once to check it out. But I thought it was cool, and they have this drone racing event nearby. So I got one from 3D Robotics, and remember how I showed you this little guy that's running the base station? This is actually what it looks like in a nice case. So I strap that to the bottom as the payload, and you can also plug in this USB Wi-Fi dongle and turn it into an access point. So you've got a flying access point. Or if you wanted to run this, you could have a flying base station. Imagine what you could do with that. By the way, I should mention on the base station, this stuff has been used for legitimate security research. One problem with GSM is that the phone does not authenticate the network. So the network will authenticate the phone to make sure you're a legitimate subscriber, but the phone doesn't check whether the network is actually legit. So you saw what network this was appearing as on your phone. You could change its codes to match that of a legitimate network. Your phone won't be able to tell the difference between this network and the legitimate one, and it will always try to log on to the cell with the strongest signal. So your cell phone will log on to this. On here, you configure it not to use any encryption, and then you can listen to everyone's phone calls that goes through here or intercept everybody's text messages. So my point is, when you're going to design a wireless communication system that will be deployed over the entire world, you should think about the security aspects of it. From the ground up. You always have to think about it from the ground up. Adding it as an afterthought never works. So this spectrum monitoring stuff that I showed you before, I was also running on here in the sky. And what I wanted to do is I wanted to get my antenna elevated up there, because then you have line of sight to all of your transmitters. You can receive so much more when you're at a high altitude. And you don't need to go on top of a building. You don't need to erect a really tall antenna mask. You just got to fly this thing up in the air, and you can usually get up much higher than you would be able to on a building anyway. Just don't annoy the FAA. It's very important. So I was running that, and that works well. I thought it would be also interesting to put a webcam on there and have a digital video downlink. When they do the races, they all wear goggles, and they have a camera on there that transmits video down via analog and NTSC. It's spectrally very inefficient because it uses up a very large bandwidth. And also, you need to coordinate on the ground so you don't interfere with one another. If you do it digitally, however, you can make all those problems go away and have it solved automatically. So Again, the webcam's just hooked up via USB. And then this is the test that we did, the initial test.
And right over there is
So that's the receiver for the video. And then the drone's all primed, ready to go. And this is sending down the video from the webcam in real time. And so it's receiving it through GNU Radio, decoding the video frames, and then showing you the live view in the corner there. And I'm just spinning the drone around so we come into view. So there we are.
Could you fly from that?
There is still a little bit of latency, and so that's one thing I'm going to work on is try and get that as low as possible. So that's the image. I know GoPro on there as well, so the goal is to make it shiny HD. We'll see how we go. So I'll just zoom through this stuff quickly. I was driving around San Francisco, and you'll probably see these Yagi antennas on street posts. I was wondering what that was. Got my own Yagi antenna, pointed it back at it, and recorded the signal. Turned out it was fast track. I went to the Golden Gate Bridge looking very inconspicuous with this whole setup pointing at the toll booth to see what signal was coming out of there. Turned out to be the same thing. So I created this little test setup and wrote some GNU Radio code to actually be able to interrogate the tag myself. Again, this is all in the open. You can point at anyone's tag and read their tag ID out of it. So here, I've got a tag behind the screen. Just put it up, and there's my tag ID that's read by the toll booths every time you go through. The interesting thing is when you go under those Yagi antennas in the street, your fast track tag does not beep. So every time you go up the 101 or pass through there, they know that you've passed through a particular point. Just keep that in mind. Or put it in a little Faraday cage. Now also you have the key fobs that are used in offices. You can use a loop antenna to look at the transactions there. This is the transaction. It uses the same kind of backscatter technology as the fast track tag. The reader will send a payload out, energize the tag will process that and send it back, and you can see what's happening there. I wanted to look at keyless entry for Priuses, or Prii, whatever the plural is. And so here what's actually happening, the way it works is that the car, you know how you don't actually need to press the remote, right? You have the remote in your pocket, you can walk up to the car, it knows you're there, and you can just open the door. What's happening is the car is constantly sending out this low-frequency broadcast saying, I'm here, I'm here, I'm here. The remote control contains a little pickup that will detect that, and then it will start a cryptographic transaction with the car to authenticate that you're actually the legitimate owner of it. And when it responds back, it's using UHF, the same frequency as if you would press the button to open it yourself. So what I did was I wanted to create a relay. I wanted to try to do man in the middle. So I wanted to be able to open the car without having the remote next to the car. So I wanted to relay the signal from the car inside and have the remote inside. So this is a setup I had by the car. It's listening on the LF, and it's ready to transmit back the UHF from the remote, wherever that might be. And inside, this was the sort of reverse setup of that. The LF is coming out there into the coil, and then if you place the remote on the coil there, it's actually picking up now what the car is sending out. So it thinks that it's next to the car. And then it will transmit about the UHF response to that. Now, I figured this wouldn't work for a good reason. And I mean, in a way, I was happy that it didn't work because it would have been a blaring security vulnerability in this entire system, which is not what we want. What actually happens, and this is also important in communication system, is the latency. So what you can see here is the blue is what the car sends out, and the red is what the remote sends back. And this all happens in a very, very short space of time. And if anything exceeds that time limit, then the system will reset and you'll have to re-authenticate. Now, with my relay approach, it took way too long for the radio packets to get from the car. I was sending it through Wi-Fi, through some IP level stuff, and then rebroadcasting on the other side. It took way too long for it to go through all that, be processed by the remote, and then send it all the way back. And so it would time out and it would start again. So, just things to keep in mind when you're analyzing the security of things or when you're thinking about implementing security later on. So very quickly, some other applications. You can decode stereo FM and RDS. Sutro Tower has lots of different FM radio stations on there. And if you pick one in particular, you can run a GNU radio decoder and then it'll tell you all the stuff there. You can also create your own stereo FM broadcast station yourself. This is obviously not one that's out there on the air at the moment. You can get traffic reports. And one interesting thing about RDS traffic information here in the States is that it's encrypted, but it's only 16 bits for the location code, and only 16-bit key. So if you want to be a little bit tricky, you can write an intelligent search algorithm to do an exhaustive search and actually then recover the keys for this nationally deployed system. If you want to listen to satellites, you just get a satellite dish, a low noise block down converter, hook it up to a radio, and then you can, this is the telemetry from one of the geosynchronous satellites over Australia. I found a signal up there on one of the transponders. And again, I went through that decoding process like with the restaurant pages, found this packetized format, saw integers and BCD and what have you. Had no idea what it was, plotted it, got some pretty graphs, but that was it. I didn't really look at it beyond that. But there's something going on there, and if you could record it over a week or a month, you could probably correlate this with some sort of human activity. You can also be crazy and put antennas on the roof of your car and drive around and actually try to pinpoint the origin transmission of a signal. So in this case, you're not actually interested in the signal content itself. You want to know where it's coming from. And so you can use interesting techniques to do that. Use GNU Radio and it'll tell you where it's coming from. In this case, this little USB missile launcher will track the position of the walkie-talkie that I'm holding. You can see there that it's following that. So the wavefront hits these antennas and it can figure out the angle of arrival. And then when I talk... and then also, you know how Google's always driving around with their cars and they have some crazy contraption on the roof of their car, usually Street View and the like? I thought, well, I'm going to put some stuff on my car and drive through the Google campus to return the favor. And so I'm going through there and it's tracking some transmission from over here. Pardon?
Don't they kick you out?
No. You can look at smart meters. You can look at, you can run this open source GPS decoder that's based in GNU Radio and actually decode the GPS signal yourself. You can receive the entirety of the amateur radio band at once. You can run that 4G LTE base station that I was telling you about. And you can also receive AIS, which is like ADSB, but for ships. And so this is the water around San Francisco, and it's just plotting all of the ships that are passing through the area. You can see here is one. It's done in a turn there, and you can see that turn tracked in the trail. So another system. You can also point your antenna like that just up into the sky. Follow a weather satellite as it passes overhead, and then you can decode real-time weather images coming down from the constellation. Here you can see the west coast of America there in this false color image that we just received with the radio. All right, so to finish up, very quickly, the Reboot project. This space probe was launched in 1978, so a long time ago. This didn't have a computer on board. It was just shift registers and sequences, no memory. It was created to study the interaction between the solar wind and the Earth's magnetic field. It was renamed ICE later on. It was a space probe of many firsts. It was put into the L1 Lagrange point, which is a special point between the Earth and the Moon where the gravity sort of cancels out, if you will, and you can have stuff dragged around as the Earth rotates around the Sun. And it was also the first spacecraft to pass through the tail of a comet. A lot of other nations had probe missions set up, but America didn't, so they repurposed this so that NASA could claim to be the first and beat everyone else. Some crazy, crazy orbits and trajectories were involved in this. One guy at NASA managed to visualize all and plan this all to the day in his head. Amazing. So we'll skip this. The probe itself is spin stabilized, so it's a spinning probe, and it has a bunch of thrusters on board, science instruments, and also S-band telemetry radio system. And if you look at it, it was when the mission finished up, NASA ran out of funding. It was put into a graveyard orbit to go around the sun, and essentially, it was forgotten about. And as you can see here, late last year, it's actually catching back up with the Earth. And some amateur radio people in Germany found its signal. The transponder had been left on. It was just a carrier, but it was appearing on their recordings. So a team got together and thought, well, what happens if we try and contact the space probe, figure out how it's doing, fire the thrusters, and bring it back into orbit around the Earth? Then we can turn the science instruments back on and actually do public science with it, which is a really cool idea. So in the ideal case, we'd fire the thrusters and then put it into orbit near the Earth. What was interesting is they raised some money using crowdfunding, quite a substantial sum, and there was a documented amount of fuel left on board the probe. Now, to make that correction maneuver, you have to be able to do it with the fuel you have left. If you wait too long, you won't have enough fuel to make the maneuver to bring it back to Earth. So we had a hard deadline. And if you look at some interesting stats, at this particular point, it's 15.5 million kilometers away from the Earth, and it's traveling at 3.4 kilometers per second toward the Earth. If you were to try and communicate with it, the two-way round-trip light time is 103 seconds. So there's quite a bit of patience you need when you're trying to talk to it. How do you talk to a space probe that is that far away? You go to the largest radio telescope on the planet. This is the Arecibo Radio Telescope in Puerto Rico. You might know it from movies as GoldenEye and Contact. Remember the beginning of Contact? No? Really cool. It's 1,000 feet in diameter. The entire structure is just enormous. This platform is suspended from these three towers. This is actually a multi-story facility there with transmitters and receivers.